I thought it'd be fun to decorate my birthday cake while I answer some of my students' questions about organic chemistry, so I hope you enjoy. Alright, so I am going to attempt to make a video of me decorating a cake. We'll see how it goes. And answering some of my students' questions. I really like making cakes. I feel like it's really zen and peaceful. And I like watching videos of people make cakes. And I was like, hey, maybe that would be a way for my students to think about organic chemistry and in a way that's like more peaceful, less stressful. And so that's what I'm doing. So the first question that I got was, is there a way to trick your brain into liking organic chemistry? So that student said that they were retaking the class and they just didn't really love it the first time. And so, like, is there a way to trick your brain into liking it? And actually another student answered, which I love, and said that she was also retaking the class and she also really didn't like it the first time she took it. But then she took biochem, and in biochem she saw a lot of the real life applications, and now she likes it a lot more. I like it when I pipe icing and the pressure of the icing will turn the turntable for me. It's very satisfying. Okay, and I actually think that that's a really good answer is, listen, organic chemistry, there's a lot of it that may not apply to you. It kind of depends on what you're going into, what you want to graduate for, whatever, what you want to do when you're done. Are you trying to go to med school? Are you trying to go into pharmacology? Are you trying to be a vet? Are you going into environmental science? So there is a lot of organic chemistry that might not apply to you, but there's also a lot of organic chemistry that will apply to you. And so if you can find the things that do go with what you are interested in and what you think like might apply to you when you graduate, you can even ask other people in your field, and some might say like, oh, it's very little, and some, but not always. There is sometimes organic chemistry comes into play. And so if you can ask the people in your field, you know, oh, okay, so how did organic chemistry help you? Or if you can, like, that's part of why I started my podcast, Chemistry for Your Life, is because I think that we don't do enough of talking about how chemistry actually does apply to our everyday life. And I think that that's really more failing on the education system. It's like, I have to teach you everything that you're going to need to know for biochem, or in OChem 1, I have to teach you everything you need to know for OChem 2. Like, my focus then becomes on getting you ready for the next class and not on how does this actually apply to your real life. And that makes me sad. I don't want that, right? Like, I want you to be thinking about how organic chemistry applies to your everyday life, but nobody asked me when they made the curriculum, you know, sadly. So I don't really get a huge say into what we have to cover in the class. But if that's part of why I started my podcast, is to try and like, okay, well, I think it's important for us to talk about this, for people to like organic chemistry or chemistry in general. So if I don't have time to do it in my class, then I am just going to make my own thing where I can talk about it. So yeah, I think that's really good advice. It's like trick your brain into liking it. That's one way. Okay, but then a different way that I also think works for me really well is I really like puzzles. And a lot of organic chemistry is just like a puzzle. And it's so annoying when you can't figure it out. This is how I feel about statistics too. It's so annoying when you can't figure it out. And you're like, ugh. But then when you do get it, it's so much more satisfying than things that make sense right away. You know, like statistics for me is a big one. I have to do statistics for my research, and when I'm doing it, I'm like, it's so hard to make sense of. And I have to like use every single piece of my brain to make it make sense. And that's hard sometimes. And that's not the other type of research I do, which is qualitative research. It makes sense to me like really easily right away. I'm like, oh yeah, this makes sense. But organic chemistry was more like statistics where it didn't make sense to me. I don't know how many students I've told this, but I actually had to retake organic chemistry because I didn't really understand it the first time I took it. But then I volunteered in the chemistry lab. I just like kind of picked a random lab, and it just so happened that they were accepting students and they were in an OChem lab, and I really liked it. I liked the lab work that I was doing, although I did not like the class. And I was like, well, I think I could do lab work like this for grad school, so I should probably retake the class and then figure it out, you know? That was like something that I was, that I realized I needed to do. So I retook organic chemistry because the first time I did so badly. I think I passed, but I think I like got as low as you could get without failing, basically like a low C. But even I didn't understand anything even with that grade. And so I decided to go back and retake it. But then the second time I took it, I had some life things happen. My mom got sick my senior year of college. And so I didn't really pay close attention to it. And then I retook it again whenever I got to grad school. And I still didn't understand it very well, actually. That's kind of embarrassing to admit, but whatever. Failure makes you better overall, so I'm fine with it. And then finally I was like, okay, I'm in an organic chemistry lab. I'm an organic chemistry grad student. I have to figure this out if I want to, you know, do this for my job, which I did. So I volunteered to be a TA in organic chemistry classes. I volunteered to be a TA in 2 organic chemistry classes. And one was Dr. Bearhays, actually, and the other was Dr. Dan DeCars. And so I sat in their class every day, and I sat, like, in the seats like I was a student, and I was trying to learn organic chemistry. And so I literally went to an OChem 1 class every single day, and then I finally got it after that. So whenever students get it the first time they take organic chemistry, I'm like, that's amazing for you. But for the students who don't, I'm like, join the club. But then I think by the time I finally figured out, it was so satisfying to like unlock that in my brain. That was where I was going with this story. That I wanted to keep doing it. And I was like, I did it. I did something really hard that I didn't think I could do. And I had to take all these like really hard tests in organic chemistry to like prove that I could get my PhD in it. And I was really worried about them because I knew my background wasn't good, but I did it. And it was so satisfying. And so even though originally I took organic chemistry because I loved the lab and I was not good at the class and I was annoyed by the class, I became someone who really liked the class and the content because I just didn't have the opportunity to learn it well. And I don't know that I had the best teachers straight out the gate, right? And so that's part of why I'm so passionate about teaching organic chemistry and why I want to make it as accessible as possible to my students is because it can feel really frustrating, but when you get it right, that is just like one of the most satisfying feelings. So I hope that answered your question. And now I'm going to pause and put this in the fridge so it gets like a nice cold solid layer before I put the next layer on. The next layer of icing on before I start decorating. Okay, the next question that somebody had was, were there times you questioned your major, like whenever you weren't sure about, or like when classes like organic chemistry got really hard or things like that? Because a lot of grad schools expect A's and B's, and it can be hard to keep going when you're getting those. That was the question. And I just want to say yes, 100%. There was times I questioned my major. So I was a chemistry major because I loved chemistry in high school, but I think college is a time when you're trying to figure out like who you are and, you know, what you want out of life. And there's a lot of times I questioned like, I think I was able to make it through college okay, because even though there would be like a few classes where I got C's, you know, like I think I got a C in biochem, I think I got a pretty low grade in OChem. I really wish I remembered what it was. It gets mixed up because I retook it. But I knew that, well, one, I did a lot of research as an undergrad, so I figured I'd still probably be able to get into grad school. I think my sister encouraged me in that too. Is grad schools aren't just looking at your grades. Like, they want you to have a high grade, but they also want you to be well-rounded. And I also worked in school, and I think a lot of times grad schools see that and recognize, like, oh, you were working and you were going to school and you still got pretty okay grades. You know, my overall GPA was still pretty good. But when I questioned the most was in grad school, actually. I even remember a time when I was talking to my roommate at the time. Today's my birthday, and I don't know why I want to talk about OChem and decorate a cake on my birthday, but that's what I wanted to do, okay? But she has the same birthday as me, so it's her birthday today, too. And I was crying because grad school was so hard, and I didn't know if I could do it. I was like, I genuinely don't even know if I like chemistry. I thought I did, but I don't know what I'm doing here. And I hate my life, kind of. And she was like, you know, what made you love chemistry in the first place? And I talked about the things that made me want to do it. And she was like, oh, I just dropped a big old thing of icing. I talked about the things that made me want to do it. And she was like, well, all those things are still true, right? And I was like, yeah. And that helped me. But then with organic chemistry, the lab I was in actually, like, I used to do organic chemistry research. So I went to a lab all day and did organic chemistry research. I was trying to get a PhD in that. And I was honestly very miserable there. Like, so that conversation with my roommate helped me be like, okay, yeah, I do still like chemistry, but maybe I just don't like these really advanced classes, and it's only for a short time, and then I'll be able to teach chemistry, which is always what I kind of wanted to do. But you have to get a PhD to teach at college, and I did not want to teach at high school. So then I was thinking, or I talked to her about that, and then I realized that I really didn't like the research I was doing in the lab. It's like, it wasn't the research itself. It was interesting, but I liked, the reason I would get out of bed every day was because of the students that I was TAing for. And I just realized I was really unhappy. And I went back and forth for a really long time about what to do. And so when you ask, like, do you ever think about giving up? I literally gave up and quote unquote gave up. I decided that wasn't the right fit for me, and I needed to change so that I could enjoy my life. And I switched to education research, and education research is where I learned a lot of the things that I use to teach now. And so sometimes I think we get really scared about changing our plans. But if you're not happy where you are right now, if you're not happy in your major, if you're not happy in your program, it's okay to think about if you want to stay or not. So, like, one of the times that I thought about if I wanted to stay or not, I decided, like, yeah, I like chemistry, and I do know that I ultimately want to do chemistry, and so I'm going to stay in this organic chemistry lab. And another time, later on, when I had the opportunity to switch to education research, I was like, okay, well, I don't love the lab I'm in right now. I was really depressed. I would, like, sometimes just drive to work and cry and then drive home and not ever get out of my car when I was working in the lab, because it didn't make me really happy. And so at that time, I decided that I would change. And so I think it's really good for us to investigate, like, how am I feeling about what I'm doing right now? Do I want to keep doing this? Do I want to be a doctor? I had a student who I'll never forget, like, came into my office hours and was crying, and she said she didn't like any of her classes. And I was like, if you don't like anything you're doing, maybe, she was pre-med. I said, if you don't like anything you're doing, maybe you should consider not being pre-med and explore other things. And she cried and said, you don't think I could be a doctor? And I was like, I think you can be, but at what cost? You know, like, that was my thought. I was a little gentler with her, but So I guess I would give that same advice, is like, if you're unhappy and you're not getting the grades you want, is it because you have other life things going on and you're really doing your best but you like what you're doing? Then I would say keep going. And that was the advice that my mom gave me when I called her when it was really hard, in organic chemistry too. In organic chemistry also, when I was in the lab. But then, is it really hard because you don't like it and you're not really interested? Then maybe you should consider switching gears. So that's one thought. It's okay to question, I think. And it's important to question, because one way or another, if you get this degree, that's the jobs that you're going to be pursuing. And if you don't like any of the classes, well, how do you know if you're going to like the jobs? And some of the jobs are really different, so, but I think it's good to ask those questions. One student just asked if I would make the video even if nobody asked any questions, because I, asked y'all for questions, or for those of you who are not my students who are watching, I asked my students for questions on this, and I thought that was nice. So shout out to her, and here's just a video of this cake spinning. I could try to get it a little bit more flat, but I'm going to try one of those like really roughly piped cakes, and I feel like it's gonna look fine, and it's my birthday cake, so I get to decide how it looks. Okay, well, I was very excited for the piping part, but it turns out that I didn't get a lot of the piping in the camera. But it is still really satisfying when I do get it in the camera. And I was kind of having a hard time answering questions and making the cake at the same time, or like piping, because I was having to make design choices, and that was hard. So I'm just going to let you see what's happening in the background with this cake, and I'm going to answer your questions separately. Okay, so the next thing I got asked about was aromaticity, and this is for my Organic Chemistry 2 class, so I'll just go ahead and answer about aromaticity. So when I think of aromaticity, first I think of it in terms of like, here's where I decided that I hated this cake design, and I completely started over. So you can see me just like totally scrape this cake, which I think is honestly kind of satisfying too. I'll do this again, and then before I pick my final one, you'll see it ended up taking way longer than I thought. So when I think of aromaticity, I think of anti-aromaticity, aromaticity, and non-aromaticity. And anti-aromaticity is unusually stable, and it has these 3 requirements, but it's special. So it's special and it's good because it's super stable. And then anti-aromaticity is special and it's unstable and it's bad. And so if it's neither of those two, it's non-aromatic. So aromaticity has these 3 conditions that you have to meet. Does it have an unbroken ring of pi orbitals? Does it have this unbroken ring of pi orbitals, 4n plus 2 pi, or the quote-unquote right number of pi electrons? And then does it have a planar shape? And so it always does if it can. The only exception is 10-aniline, because it's just too much steric hindrance. For anti-aromaticity, it actually has the same requirements. Anti-aromaticity needs to be... Oh, wait, there it was. I decided I didn't like it, and I went with a whole new thing. I didn't record me wiping that one off. But my camera angle is not great for this part, so you don't get to see as much as the piping as I wanted. But you'll still get to see me make the cake, so hopefully it's still fun. Okay, so anti-aromaticity has the same 3 conditions, only the right quote-unquote number of electrons changes. So you still need the unbroken chain of pi orbitals. You still need it to be planar. But instead of 4n plus 2 pi electrons, you end up having 4n electrons. So 4n pi electrons. So that'd be 0, 4, 12, 16, just in increments of 4. And then and that's bad. Things don't want to be anti-aromatic. So if they can get away from anti-aromaticity, they will. And the 2 ways things can kind of get out of aromaticity, if they have the right, like if all those conditions are met, there's 2 things they can do to avoid it. And one is if they're bigger than, if it's 8-membered carbon ring and up, they'll bend out of planarity. So they'll bend to try to not be polar. They'll bend to try to not be anti-aromatic. Or if it has a lone pair on it, the lone pair might be able to hybridize into an sp3 hybrid orbital, and so then it breaks the ring of pi orbitals all the way around, and now it's non-aromatic. And this kind of brings me then to somebody asked me about, so like, what do we do about lone pairs in general? So lone pairs will do what's best for them and what's best for the molecule. So if they can hybridize into sp3 hybrid orbital to avoid anti-aromaticity, that's good, and they'll do that. But if they can go into a pi orbital, and that goes into the right number of 4n plus 2 pi electrons and make something aromatic, that's good too, and it'll do that. And so really the lone pairs will do whatever works best for them, and what works best for the whole molecule. So pi orbital in conjugation or sp3 hybrid orbital to avoid anti-aromaticity. But then something else to think about with those pi orbitals or with those lone pairs is there can only be one lone pair in a pi orbital per atom. So if I already have, the only place we've really seen this is with nitrogen, a heteroatom that has a pi bond already on it. The lone pair on that atom can't go into aromaticity, because if it went into a pi bond, it's not in conjugation, it would be perpendicular. So and then there's radicals, which radicals are just one individual electron by itself. So you can sort of think about that's always going to be an odd number, so they won't be aromatic or anti-aromatic. The other question I think was about carbocations or just positive charges in general. So that's a good point, is there might be a lone pair on a neutral atom, and there might be a positive charge on an atom with 4 things on it. So instead of just assuming it's positive, so there's an empty pi orbital, which is the case with carbocations, but if it's nitrogen, it has 4 things bonded to it, it might be sp3 hybridized. So anytime you see a positive charge or a negative charge or whatever, I would use formal charge, which is the thing you learned at the beginning of OChem 1, where you look at the number of valence electrons, and then you see how many bonds and lines are around that thing, and that's how you get the formal charge, but do it backwards. So if there's a negative charge on a carbon, we typically know that means there's a lone pair. If there's a positive charge on a carbon, it's because carbon needs 4 things bonded around it, so it must be missing something. But nitrogen has 5 valence electrons, so it wants 5 bonds or 5 things around it. So if it only has 4 bonds, it's positively charged. So I guess for those, that's one of those cases where I talk about, like, it's probably a good idea to think about, like, what, for every individual case, don't just memorize it, but think about what's going on here. What are we doing right here? What's happening with this atom? What's its formal charge? Why is it negative or positively charged? How many valence electrons does it want? Instead of just memorizing cases. And then the very last question I was going to address was aromaticity and acidity, and aromaticity and basicity. So again, basicity and acidity are a lot about lone pairs, electron acceptors and electron donors, right? And a lot of times we're losing a hydrogen, and then an electron pair gets left behind that the acid has to, quote unquote, accept. And so the question is, how well can that molecule deal with the lone pair? Well, if the ring is a continuous ring of pi orbitals except for that hydrogen that then is given up and leaves the lone pair behind, and therefore the atom goes from being not aromatic to being aromatic, that's good. And so the lone pair is happy because it makes aromaticity happen, right? So that's something that you're like, oh, great, this lone pair makes aromaticity happen. That's awesome. So it's more willing to give up that hydrogen if that happens. But if the opposite happens, you give up that hydrogen, you accept a lone pair, and now we have 4 N pi electrons, and then it'll hybridize out to avoid anti-aromaticity. That's not as good, so it'll probably just be the acidity that you would expect. But in the other case, you would have a hydrogen that's more acidic than you would expect because the lone pair is so easily managed by going into aromaticity. So if by giving up a proton and gaining a lone pair, the molecule becomes aromatic, then that's good, and it will be more acidic. If
that's not what happens. And by giving up a lone pair and going into, like the lone pair going into the ring makes it anti-aromatic or non-aromatic, then it would be about the acidity you would expect. The opposite is also true for basicity. Basicity, if the lone pair is making up the 4n plus 2 pi, it doesn't want to take a hydrogen because then it loses that lone pair and it breaks aromaticity. But if the lone pair is not part of that conjugation, it's not part of the aromaticity, then it doesn't matter and it'll act like a lone pair normally acts. I hope that was helpful and fun to watch me make this cake, and I don't really have anything else to say, so I guess you can just watch me come to the finished product. I hope you like it. Happy spring break!